Exercise 18.5 is tying in this naming system that we're learning now with meta and with benzene derivatives like benzoic acid. It's tying that into something we learned in the ether chapter. When we talked about ethers, we talked about epoxides. Those are those ethers. Ethers are not normally very reactive, so what you can do to make them reactive is put them in a ring, and this now is really reactive because of the ring strain. These carbons are sp3 hybridized, so they want to have 109.5 degrees in between all their bonds, but if you force this in a ring, they only have 60 degrees between that bond, and that makes these rings really unstable. There's a lot of ring strain. They want to pop open. So these epoxides were ways of making ethers reactive by putting them in rings. So they're really useful, especially if you want to put two functional groups right next to each other, because you can have another nucleophile come in. Oops. You could have a nucleophile come in with some sort of functional group on it, and that can attack that carbon, which is slightly positive, and break the epoxide open. So you'd have a functional group here, where the nucleophile was, and a functional group on the other carbon, where the oxygen is going. So we saw that in chapter 14, that the epoxides are really useful in the synthesis. And you can make them using peroxy acids. So you can make these things from alkenes using peroxy acids. Let's break that down, the concept of a peroxy acid. So the most common acids in organic chemistry are something called carboxylic acids. Those have a carbon double bonded to an oxygen, single bonded to an OH. And the reason why those are common is because they're made of elements that reappear so much in organic chemistry. These elements are very prevalent on the surface of the Earth: carbon, oxygen, and hydrogen. Oxygen and hydrogen in particular. And what can happen is, in this structure, the arrangement of these, if the hydrogen leaves, that's what would make this acidic, the electrons that were in the bond end up being allylic to the double bond here. And so they're spread out, and the negative charge on them is stabilized through resonance. So because that conjugate base is stable, that molecule is able to give away its H, and so that makes it acidic. So these are the most common acids in organic chemistry: carboxylic acids, carbon double bonded to oxygen, single bonded to an OH. Now those have two oxygens. If you add even more oxygens, then it becomes peroxy. It becomes a peroxy acid. So if you stick an extra oxygen there, it becomes a peroxy acid. The prefix per means a lot. For example, in the word perfect, the fect means done, and the per is a lot. Like, it's completely done. There's nothing else you could do to that. It's perfect. So a peroxy acid has a lot of oxygens. There's the normal amount of oxygens, and a peroxy acid you have even more oxygens. And so that's the structure they're giving you here for peroxy acids. So MCPBA is metachloroperoxy benzoic acid. We're going to have this sort of peroxy structure in there. But if you wanted to draw what MCPBA looked like, the first thing you'd want to do is to start with the backbone, benzoic acid. What does that look like? It's a derivative of benzene, so you draw the benzene ring. And then it's a benzene with a carboxylic acid coming off. So there's your benzoic acid. But it's not just benzoic acid, it's peroxy benzoic acid. So we have to stick that other oxygen in there. So there we have peroxy benzoic acid. That takes care of the P, B, and A, peroxy benzoic acid. And then you just need the meta-chloro. Well, now we know what meta means. It's 1,3. So this is 1 because it's the peroxy acid that's giving this backbone its name. And then you can number it however you like. On the third carbon, that's where you'll put a chlorine. So that is meta-chloro, 1,3 chloro, metachloro, peroxy benzoic acid. The structure for it right there. That's the MCPBA that is so useful to use when you're trying to take alkenes and add two functional groups next door, first by making an epoxide using MCPBA, and then reacting this with a nucleophile that'll break the ring open.